LeetCode has a very famous problem where you are given two arrays A and B and you are allowed to swap two elements at the same index in one operation. So you pick an index I and you can swap the element that is present in the first array with the element that is present in the second array. And your goal is to find out the minimum number of swaps that you need to make such that both the arrays are sorted in increasing order after you have done all the swaps. Now, if you look at the editorial for this problem on LeetCode, or even if you look at the discuss section for LeetCode, you will see that all of the solutions use dynamic programming. And in fact, when you see this problem for the first time, you can immediately recognize it as a dynamic programming problem because the solution with DP is very obvious. You have only two choices for the ith index. Either they will be swapped or they will not be swapped, and then you can do some case analysis to figure out the final DP entries. All that is fine, but I always wondered whether there was a different way to interpret this solution, maybe without DP, and even if DP is being applied, can we have a different interpretation? So all of that changed when this problem appeared in a recent Codeforces round, and not this exact same problem but a variation of this problem. And in the Codeforces problem, you are given the same setting, like you have two arrays and in one operation you can pick any index and then you can swap the uh, elements present at these indices. And the Codeforces problem was asking you that instead of trying to minimize the number of operations, give me the subset of indices that you can choose. So for example, if you choose this I1, I2 and I3, and even if after swapping the elements at these indices, if the array is still sorted in increasing order, then that is a valid subset. So the Codeforces problem is asking you to find out how many such valid subset of swaps exist such that after these swaps are done for the indices that you have selected in your subset, both the arrays should be strictly increasing. Now, of course, even the Codeforces problem sounds like straightforward DP, and it is. You can implement a DP solution just like I told you, where you make two choices at each index. So you maintain a 2D DP, and the second parameter will just be 0 or 1 depending upon whether you have swapped this ith elements or not. But in this video, I want to show you a different way to approach this problem. I'm not saying that way is easier or better to understand, but it's just a different line of reasoning, and it's always good to know and learn different things in competitive programming. So I'll show you some new techniques to approach this problem. So let's start with the Codeforces problem first, and then we'll come back to the LeetCode problem. So if you have these two arrays, the first we'll do a series of transformation on it. So the first transformation that you'll do is you have A and B. Then let's say that B stands for big. Let's have this notation so that you will remember throughout this video that B is the bigger array. Then what we'll do is for each index I, let's make sure that all the big elements go to B and all the small elements remain in A. For example, if at index 4 A contains 5 and B contains 3, then you swap these two elements and you make this array 3 and 5 at this position. If at index 7 A contains, let's say, 9, but B contains 12, then you don't touch this element at all. So after you do all of these transformations, you move all the small elements to A, move all small to A, and you move all big to B. That is how you remember that B stands for big. Now you will realize that, so this is the first transformation that we have done. Now after doing this transformation, first let's see whether the array will be sorted or not, and if not, what are the consequences. So once you have done this transformation, you can assume that this is A and you can assume this is B, and we know for sure that AI is less than BI. Okay. So with this transformation, you can see that the array has the best chance of being sorted. Why am I saying that it has the best chance of being sorted? Because you have clubbed all the bigger numbers over here. So let's say you have 5 and 9, 20, 30, 100, 200, and so on. All the big numbers are over here, and all the smaller numbers are over here like 2, 3, 11, 22, 90, and 100. So you can see that right now this is sorted. But if this is not sorted, if this array is not sorted, then we claim that the entire thing, no matter how much shuffling you do, it can never be sorted. Why is that? Because you have a small number over here and you have a big number over here, and you have small 2 and you have big 2. Then if this array is not sorted, then small 1, this left side will be greater than the right side. However, if you were to swap this small with big, even in that case, big is already small, big is already greater than small. So if this number is greater than this number, and if you swap out this number with an even bigger number, that equality will still hold. For example, let's consider a concrete example. Like if you have 5 and of course you have a 9 over here, then if the array is not sorted, you will have something like 3 over here. Then if you have this configuration, then if you replace this 5 with 9, even in that case you can never make the array sorted. Right now was your best chance because you were comparing 3 with the smallest number that exists on the left hand side. But if you try to make it even bigger, then you lose your chances to make the array sorted. But okay, you might argue that what if instead of swapping these two elements, we could have swapped these elements? Wouldn't that have made the array sorted? No, because if these two elements are violating the condition 5 and 3, then if you place 3 downwards over here, then 3 was less than 5, but since 9 is bigger than 5 and the bigger elements always live towards the bottom, then 3 will also be less than 9. So no matter what you do, you can never sort the array, and sorting is not possible. So this is one way to check whether an answer actually exists or not. So this is one technique that you can learn, that if you if you have a chance to make the array sorted, then definitely if you keep all the smaller numbers in one block, in the first array and all the bigger numbers in the second array, then this one this resulting arrays should be sorted amongst themselves. So now that we have concluded this, let's see why does doing the reordering of the array elements does not change the answer for the Codeforces problem. So right now we just said that pick any index I and then swap the elements here and here to make sure that all the bigger elements land in the B bucket and all the smaller element lands in the A bucket. So the initial swapping does not matter because anyway you have to compute the subset of indices where you have to do the swaps. So suppose the elements that you have already swapped in the first round even before solving the problem to make sure that all the big elements go over here. Suppose those set of indices were not supposed to be swapped in the final subset. So that is fine. You can, in the final subset that you create, suppose after doing the series of swap and creating a new version of this problem where you have all the smaller elements here and all the bigger elements here, you conclude that in this new configuration, this element, and this element forms a valid series of swaps. So what you can do is you take all of these indices I1, I2 and I3 and you can just append all the initial indices that you swapped for the subset. And if you indeed swap this I itself, then you can turn it off from there. So in fact, this configuration that you have done, that covers all the 2 to the power n possibilities. So take a minute to convince yourself why that is true. Now that we have that out of the picture, now let's see how to solve this problem in the reduced setting where you only have a big element, a big array and a small array. So let's say this is your small array and this is your big array. Now let's look at this particular index I and this index I plus 1. Now at this position, the maximum value lives over here. And at this position, the maximum value lives over here. Now, let's assume some initial values to make the understanding clear. Like let's say it is 3 and it is 5. And on the right hand side, what are the possible values that can be? So the maximum value is 5. Then if the minimum on the left hand side, which is this block, if it is greater than the maximum on the right hand side, which is this block, then no matter what element you keep to its left, it will always be sorted. For example, if this number is like, let's say 7. So if this number is 7, like this cross configuration, so this is the minimum and this is the maximum. So if this minimum itself is greater than the maximum that is possible on the LHS, then no matter if you have this configuration, the first array will still be sorted. And even if you have this configuration, the first array will still be sorted. In fact, the second array will still be sorted. And why do I say that? Because remember that big is greater than the small. So this means if this is 7, this has to be something that is more than 7. So if this number alone is greater than both of these, then this number alone should also be greater than both of these. So this means that as long as you have this element is free to do whatever it wants. It can either be in the configuration 3.5 or it can be in the configuration 5.3. So what about the other case where this minimum over here is not greater than the maximum? Because if this minimum is greater than the maximum, we know that this left side is allowed to vary freely. But the second case where the minimum is not greater than the maximum, so let's take an example. You have 3, you have 5 and now you have 4. And here you can have anything which is greater than 4, right? Doesn't matter. So you will notice that since this cross inequality is not satisfied, means that they have to retain this configuration only. None of them can flip over, because if you try to flip over this part, so this part is empty and this part is 4, this part will not be sorted. But if you try to flip over the left hand side, then you will have something like 5, 3, 4 and whatever is here. Then this part is not sorted. So this means that these two are now clubbed together. They will, this element that does not have a choice. It has to stay stuck to this element. So you can think of it as forming a connected component. So if this is one element, this gets attached to this element. So if you follow this reasoning, you will realize that each element, this, if this is an element I, if this is an index I, then it will form a connected component, where a connected component means that the cross inequality is not being satisfied, means the minimum on this side is not greater than the maximum on this side. So this means that they have to stick together. Similarly, this will also form a connected component with this, like they have to stick together, and then they have to stick together, and then they have to stick together. And then there will be some edges where this element, the minimum over here, is greater than the maximum over here. So let's create the edges in green color, and let's call these edges as the type 1 edges, and the red edges as the type 2 edges. You can see that I have marked these as red because they are tightly coupled with each other. None of them can vary, but the greens one can vary as much as they want. So now, once you do this split, you will realize that the array can be split into blocks. So this is one block, and then this is the next connected component, then the third connected component, fourth connected component, and so on. And you will realize that inside one component, you cannot change anything, right? Because all of them are tightly coupled with each other, because the cross inequality for the minimum being greater than the maximum is not satisfied. Means that your answer will only be the connecting points of these, uh, basically the starting points of these connected components. So the total count of elements that are inside of these connected components, they cannot vary freely. But apart from that, everything that is colored as green, they can vary freely. So that is why the answer is simply 2 to the power number of blocks, right? Number of connected components. Number of connected components. So to implement this, you can see that we just iterate over all the AIs and BI, and we make sure that the bigger element always lands in the B bucket. And then we try to find all the type 2 edges. So type 2 edges, basically they will become the starting point of the component, because here you will see that this is A, this is B. So we are saying that this BI, so this BI, and we are comparing against this A of I plus 1. So this means that if this number is smaller than this, it means that it is tightly coupled with this. So that's why it is a type 2 edge. So we are computing all the red edges, and then the total number of connected components would be n minus the red edges, and then all the other elements that are not on the connected component, or basically the starting element of that component, they can vary freely. So that is why the answer is 2 to the power number of components. So in this manner you can solve the Codeforces problem, and of course you can also solve it with dynamic programming. This is just another insight into that problem. And so far we have discussed that doing that initial reordering of making sure that all the big elements go into B, that does not affect the answer to the Codeforces problem. And if an answer exists, then your best chance of reaching that answer is by doing this reordering, so that all the smaller elements are together and all the bigger elements are together. Now coming back to the Codeforces problem, coming back to the LeetCode problem. So in the LeetCode problem, now you have to figure out the minimum number of swaps to make the both the array strictly increasing. So you can apply the same technique here as well. So in the LeetCode problem, you have to find out the minimum swaps. So let's say you have A and you have B. So you do the same technique, like you make sure that all the elements first land in the B bucket. That is, if you have this AI where AI is greater than BI, so you do the swap first. And you might wonder that LeetCode was asking you to minimize the number of operations, so why are you doing any unnecessary operations on it? That is fine. You do the swaps, you bring all the bigger elements down and you keep all the smaller elements up, and then we will later do the adjustment. How will we do the adjustment? We will remember that okay, we have done the swap, but if this swap wasn't really needed at the end, we'll remove it. So once you have done these adjustments, now it is very easy to think because all the smaller elements are here and all the bigger elements are here. And then you can see that the same logic still applies. You can still split it into connected components, right? And all the elements that were allowed to vary freely. And in the Codeforces problem, you took it as 2 to the power component count, right? So in the LeetCode problem, all you have to do is make sure that all the components that are allowed to vary freely, you don't let it vary, so that you can minimize the number of operations. And then after you have decided the orientation of each of the elements, you can check whether the initial swap that you had done, whether that can be removed or not. How can you check that? Because if this element is indeed free, if it creates a type 1 edge, then you could have as well reduced, as well you could have as well not done the swap, and then still the conditions would be valid. And another thing that you have to keep in mind, that we said that while doing the swaps, all the bigger element has to land in the B bucket. So in the Codeforces problem, it did not matter, but in the LeetCode problem, it can matter, because when you are doing the swaps, then like what if there was a solution where you had done the swaps where all the bigger element land up and all the smaller elements land down. So to accommodate this case, that should be easy. Like each connected component that you are creating, right? You can say that either you have this connected component as it is along with the initial swaps that you have done, or you flip everything around. So the answer would simply be the connected component dot size minus whatever the count that you have so far. So the implementation would look something like this. You traverse, first of all you do the swap to do the normalization. Like for each index I, if AI is bigger than BI, then you do the swap and then you record that okay, at this index I have done the swap. And then you iterate over each of these elements, and then you figure out if this is a type 1 edge or type 2 edge. And then depending upon that, either you keep on increasing the count of the connected component, or if you know that one component ends over here, then you can decide whether to keep the component in this order or flip it around. So that is what we have done. Either you keep it as it is or you flip it around. And this way you can solve the LeetCode problem as well. Now, I'm not saying that this approach is easy or simple to understand or anything, and I'm not even recommending you to use this approach should you see this problem in an interview. But this was just an interesting perspective that I saw and I wanted to share. So let me know if you have any alternate solutions. Let me know in the comment sections. Thank you.